Let's start. So today's topic, which is the three-phase instantaneous power. So it's very similar to what we know from chapter 7, instantaneous power and complex power for single phase. But what we will do is we will apply this 3 times. One for phase A, one for phase B, one for phase C. Then we will see how is the relationship. Will it make the problem simpler or will it make it more complicated? And we will see some definitions like the power of phase A, the power of phase B, again, power of phase C, and the total three-phase power, which is basically the sum of these 3. Now, instantaneous power, recall it is for the single phase, which is V times I cosine 2 omega alpha, plus alpha plus beta, plus VI cosine alpha minus beta. So there was sinusoidal term, and there was a constant. And that constant, we used to say this is the average power. Or in other words, this is the real power. Okay? That was in the instantaneous power. And then the function used to have 2 components, sinusoid components changing with time, and the other component which is the fixed. Now, we need to apply it for the 3-phase, so we need to apply a power that's associated with each phase. So there's a power of phase A, power of phase B, power of phase C. The same magnitudes, but the differences are in angles. So you can see what's inside the cosine and the angles. So what will happen in ABC sequence if we assume balanced? I can write it down. If balanced, what will happen? We can say alpha of phase A equal alpha, beta of phase A equal to beta. I'm going to assume it as constants. Then I'm going to assume it also as a positive sequence, ABC sequence. Therefore, alpha of phase B will be alpha minus 120. Beta of phase B will be beta minus 120. That's the relationship between the angles of these 3 phases. Then alpha of phase C will be alpha plus 120 degrees. Beta of phase C will be beta plus 120 degrees. Okay? How can we use this into these expressions? We can say alpha phase A minus beta phase A will be alpha minus beta. Alpha phase B minus beta phase B will be alpha minus beta. Then there is 120 minus 120 minus 120. They will cancel each other. It will be alpha minus beta. Alpha phase C minus beta phase C will be alpha minus beta. So 120 and 120 will cancel each other because we are subtracting. Okay? So we realize the constant parts, which is V times I cosine alpha minus beta, all of them will lead to the same value. Alpha minus beta, cosine alpha minus beta, cosine alpha minus beta. They are all the same magnitude. Then they will be all with the angle. When you subtract the angles, the phase shift will cancel each other. Okay? So, as a result, if you sum all of those, because we have a definition called total instantaneous power, basically you need to sum phase A plus B plus C. Then when you sum the constant parts, it will be 3 times the constant parts. Because again, phase A equal phase B equal phase C. The power will be equal to each other if and only if balanced. This is if and only if balanced. Or if balanced. But what will happen to the other part, which is the sinusoid part, inside the cosine 2 omega plus 2 omega t plus alpha plus beta? So the relationship between alpha plus beta, I can write it here, alpha phase A plus beta phase A equal alpha plus beta. Alpha phase B plus beta phase B will be alpha plus beta minus 240 degrees. Alpha phase C plus beta phase C will be alpha plus beta plus 240 degrees. Okay. What does this mean? When we want to sum all of these three phases, phase A plus phase B plus phase C, they are all the same magnitude. The difference is in the angles. So the angles, when you try to plot the vectors, alpha plus beta will be like this. Alpha plus beta minus 240 will be like this. Alpha plus beta plus 240 will be like this. So what will happen to the value? Imagine there's an object and there's a force with each angle. What will it be? What will it be? We need to calculate the net force and the object in the origin or in the middle. If there is a net force, they are all the same magnitude. The net force will be 0, right? Yes, it will be 0. So as a result, when you do the sum, this part will be 0, while the other parts will be 3 times VI cosine alpha minus beta. That's the key. That's the point. As a result, when we do the total instantaneous power for the phase A plus phase B plus phase C, it will be 3 times VI cosine alpha minus beta. So I can rewrite it here as total instantaneous power if unbalanced. You will say P three-phase equal of T here equal P of phase A plus P of phase B plus P of phase C. So use the general formula. Calculate phase A alone, phase B alone, phase C alone. While if balanced, you will say P three-phase will be 3 VI cosine alpha minus beta. That's it, direct. Keep in mind, when it is balanced, you will not see the time. It will be only constants. Constants, no time. Even though it's instantaneous power, that the power right now, not the power that of average power, it's not average power, but we see that there is a nice property for the three-phase. When we need to calculate the instantaneous power, it will be constants. It will not be fluctuating like a sinusoidal waveform. So what you are consuming right now, it's constants. And that's very practical. That's what we are using in daily life. That's why we say like three-phase generator has that amount of power, that amount of like the load overall, like they're basically most likely when we discuss the load for the grid, we mean like the total three-phase power, okay? So anytime the default, when you read about any three-phase system, when you see anything related to the power, this is the total three-phase, unless there's something tell you that this is of phase A, phase B, phase C, or whatever. But the default, when you see any power for any three-phase system, this is the total three-phase power. Again, the summary here, if you are dealing with the unbalanced system, calculate with each phase alone. If you are dealing with balanced, you don't need to calculate for each phase, just do the total 3 times V times I cosine alpha minus beta. Okay, any question? Now let's go to the complex power. So total instantaneous power that was related to time domain. Now in phasor domain, we used to have like S bar, which is the complex power, equal V times I conjugates. That's the famous formula that we used to do in single phase. Now in three phase, we will do the same, but for each phase alone. So SA equal VAN times IA conjugates, SB equal VBN times IB conjugate, SC equal VCN times IC conjugate. Then the total complex power will be the sum of those. So those relationships are valid anytime. Valid anytime, even if unbalanced. So So if it's balanced, unbalanced, whatever, they are valid. So if you need to calculate the power for each phase, calculate phase A, calculate phase B, phase C, then say find the sum. This is the total three-phase power. However, if the system is balanced, we can do some shortcuts. We can make the life easier. How? If the system is balanced, you need to calculate, remember, if the system is balanced, we will convert three-phase to single-phase. We will take phase A as a reference. Then you will calculate the power for phase A alone. How about phase B? The same as phase A. How about phase C? The same as phase A. So they all will equal to each other. How about the total? 3 times phase A. 3 times my reference. So the advantages of three-phase, if it is balanced, you will convert three-phase to single-phase, as we discussed earlier in last lecture, right? We already converted three-phase to single-phase. Then, from that single-phase, what you need to do is to convert or to calculate the power for phase A. After that, on phase A, you need to, when you calculate the power for phase A, you can say phase B, phase C, they are equal to each other. So, if it is balanced, again, this is if and only if balanced. So as a result, we will end up, this is the derivation, so I would say like S of phase A equal to S of phase B, S of phase C. Then, to find the S three-phase, the total three-phase, will be 3 times SA. Or in other words, sometimes we say 3 times S single-phase. Because single-phase is most likely associated with phase A as a reference, so whatever we can call it, that's what it is. Keep in mind, this is balanced, if balanced. If unbalanced, this is not true. What should I do? Calculate for each phase alone, then do the sum. Okay? Does this make sense? Okay. So in summary, if it is balanced, the power of three-phase will be 3 times the power of single-phase. Then it will be 3 V times I conjugates. We know V times I conjugate, but we will add the number 3 just as an indication if it is three-phase. Then to calculate the real power, we know how to find the real parts, how to find the imaginary parts, convert rectangular or polar to rectangular coordinates, and just do, you don't need to memorize too many formulas, but I mean, you can find, calculates or converts the rectangular to polar, polar to rectangular. Then you can find the real part, imaginary parts. So it is like even S three-phase angle theta. Okay? So how to calculate S single phase? S single phase, it is S three-phase divided by 3. And it is the same as phase A, the same as phase B, the same as phase C. Sometimes, again, as a shortcut, we call it S single phase, or sometimes we call it S phase A. Because recall, last lecture, when we do our analysis for balanced system operation, we used to assume the system or convert three-phase into single phase, which is by calculating the per phase equivalent circuits. Do you remember this? Finding the per phase equivalent circuits. So the procedure in the past, converting delta to Y, then find the per phase equivalent circuit. It will be taken phase A as a reference, calculate the currents or the voltages, whatever you need. Then after that, if you need to calculate the power, you can calculate the power of that reference. After that, how about phase B, phase C? The powers will equal to each other. The total three-phase power will be 3 times the powers. Any questions? Okay, let's go source for examples. So that's what we need to know, because we know the complex powers, we know the instantaneous power, we know V times I conjugates, but here just times 3. That's the thing. So we have a 48 volts, three-phase system with a Y impedance, 8.66 plus J5. We already solved this example, right? Last lecture. Here, we will need to add extra thing, which is we need to calculate all of the complex powers. How can I solve this example? Let me go back one step to the last lecture when we calculated, this is the same as that example. But we will say like part A, calculate the currents. Part B, calculate the power. Let's just make a quick recall. How did we calculate the currents? So we said 480 volts, no information about it, then this is line to line. Then we will calculate V line to neutral, which is V line to line over root 3. Then it will be V 277.1. Then VAN will be V line to neutral angle 0. That's VAN. Then draw the circuit. That's the circuits. This is how the circuit looks like. Then we will convert 3-phase into single phase by taking phase A as a reference. Then we need to calculate the currents. How to calculate the currents? Ohm's law, V over Z, or just a single loop. It will be V over the Z equivalence, right? So V over Z, this is the currents. How about the other currents? IB will be like, since there is no information about the sequence, then it is positive sequence. Then make a phase shift negative 120 for phase B, plus 120 for phase C. Okay? We already did this. Now, after that, we need to calculate the power for each phase. Power for phase A, power phase B, power phase C, and total complex power. So whenever we set to determine all of the complex powers, we need to calculate these 4 powers. A, B, C, and total. How can I calculate these powers? So again, here we just calculated IA equal 27.71 angle negative 30 degrees. And we know VAN we already calculated as 277.1 angle 0 degrees amperes. Now we need to calculate the power. According to the power formula, let's find phase A first. S of phase A equals to VAN times IA conjugates. We know this, right? So it will be 277.1 angle 0 times 27.71 angle negative 30 degrees conjugates. Before doing this in the calculator, do the conjugate first. So 27.71 angle 0 times 27.71 angle positive 30 degrees. So SA will be, after doing the calculation, will be 6,649.7 plus J 3,839.2. And of course, the unit is volt ampere. Okay? Now, we need to calculate S of phase B, S of phase C. What should I do? There is one approach. I can say S phase B equals VBN times IB conjugate, right? Or we can say S phase C equals VCN times IC conjugate. Is this correct? Yes, but this will take a long time. So I can say the system is balanced. So what? We can say SB equals to SC equals to SA. Then it is 66497.7 plus J 3839.2 volts ampere. That's it. I don't need to do any calculation. Here is a shortcut. Okay? That's a nice property, which is you don't need to calculate SB, calculate SC. This will take longer time. Then the best way is just to calculate it like this. How about the total three-phase power? You can say S three-phase equals to SA plus SB plus SC. This will take a long time, right? Or you can say it is 3 times VAN IA conjugates. Yes, I can say. Or simply, you can say S three-phase will be 3 times S phase A. And we know S phase A, which is 3 times 6649.7 plus J 3839.2. 3 times this value, I think it will be as 19947.2 plus J 11517.7 volts ampere. This is S, the total three-phase power. So I would say that there are many ways to calculate this, but choose the easiest way. Choose the easiest way for you. Then you can save more time, more efforts, less mathematical formats, less chance of getting any errors. Okay? Again, this is happen if and only if balanced. If it is unbalanced, you need to calculate for each phase alone, and the total three-phase power will be the sum of these three phases. Okay, any question? That was part A of that example. How about part B? Part B, it says if the load is delta, what should I do? And we need to calculate the total three-phase power. Part B, repeat if the load is delta. Let's go back to the previous example that we discussed last lecture. When we had delta, we converted delta to y. So we said zy equals to z delta divided by 3. That's what we did. Then we said, let's convert y to, or three-phase y to single phase. After converting delta to y, we redraw the circuit, then converting this to single phase. Then we can find IA by using Ohm's law, which will be V over Z equivalence. So we calculated IA, IB, IC. Then we need to calculate the power. So the power will be, we know for part B, whenever we deal with delta load. So first we convert delta to Y, then convert three-phase to single phase. Then IA was 27.71, angle negative 30 degrees. VAN equals 277.1, angle 0 degrees, which is the same numbers as this one. That's it. So you need to calculate SA. So we can say, since it's balanced, SA equal to SB equals to SC, again because it's balanced, which will be VAN times IA conjugate. So the answer will be, we calculate it as 6649.7 plus J3839.2 volts amperes. How about the total three-phase power? S three-phase will be 3 times SA. Then it will be as 19947.2 plus J11517.7 volts amperes. Okay? That's it. That's all. How about if we need to find the real power? The real parts. We know that, right? How about the reactive power? The imaginary parts. Okay, how about the power factor or the apparent power or the angle? Convert this to polar. You know how to convert the numbers to polar, right? That's it. So, I mean, the other thing, which is how to deal with the number, I'm sorry, with the complex numbers, we already know, we're already familiar with this. So there is no need to repeat how to find the real power, reactive power. You know that S three-phase equals P three-phase plus Q three-phase, JQ three-phase. Or it can be S as a magnitude, angle theta. Then we can say power factor is cosine theta. And it depends, is it lead or lagging? We know everything. Okay, any question about three-phase power? Okay, so let's do the last example about three-phase power, then we will be done with the three-phase power. I'm going to give you a few seconds to write, then we will go to the last example. So in summary, the three-phase power is something that we already know. I mean, the power, complex power, we already know it since chapter 7. But here, since it's three-phase, just times 3. or if it is balanced, S phase A plus equal to S phase B equal to S phase C. Okay, here's a question. So a 480 volts three-phase system serves 23.04 kilovolts ampere load at 86.6 lagging power factor. Determine the line currents and the load complex power. That's all. That's all what you have. So basically, when you see these kind of questions, try to analyze it step by step. Now, we have a 480 volts. Is there any information about this is line to line or line to neutral? No information at all. The default this is what? Line to line. So we can say V line to line equals 480 volts. So remember the famous formula that I told you, we will use it 100 times. So V line to neutral equal V line to line over root of 3, which is 480 divided by root of 3, then it will be 277.1. Then VAN for phase A equals 277.1 angle 0 degrees volts. Is there any information says the system is unbalanced? No information. So we will assume it balanced because no information about this unbalance. Is there any information about the sequence? No information about the sequence. So it is ABC sequence. I'm going to assume it like this. How about the power? We know the power 23.04. Is there any information? This power for phase A or this power for phase B or this power for phase C? No. So this is the total three-phase power. So we will say S three-phase load 23.04 kilovolt ampere. Again, how did I know this is S, not P, not Q? The units, right? Unit volt ampere. Then we have theta, which is 0.866 lagging power factor. Okay, so what should I do? How can I calculate the currents and the complex power? This is the load for each phase. Then again, the total complex power that's given is the complex power that's given is the total complex power. So we need to calculate the total three-phase power. The total three-phase power is actually the magnitude and the angle. The magnitude is already given as 23.04 times 10 power 3. Then the angle is what? We don't know the angle. So it can be plus or minus cosine inverse of power factor. I think this is the power factor, not theta. Now, 23.04 times 10 power 3 angle. Since it is lagging, it's going to be positive. Cosine inverse of power factor, the power factor which is 0.866. So the answer will be 23.04 times 10 power 3 angle cosine inverse, which is 30 degrees volts ampere. This is the total three-phase power. Now we know the total three-phase power and we need to calculate the other power. So the power of phase A equals to the power of phase C equal to the power of phase C, which is the three-phase power divided by 3. So this number will be divided by 3, and then the answer will be 7.68 times 10 power 3 angle 30 degrees volt ampere. And remember, we need to convert this to rectangular coordinates. So in order to convert it to rectangular, it will be 6.65 times 10 power 3 plus j 3.84 times 10 power 3 volts amperes. Remember, this is for single phase. Now, how about the currents? Or even, I forget to write the three-phase power here. 19.95 plus j 11.52, all of it times 10 power 3 volts. I just wrote the expression into rectangular coordinates because that's what we need to do. Yes?
Is there a difference between lowercase a, b, and c and uppercase a, b, and c or no?
No, it should be the same sign, just like maybe typo mistake, so it should be fine.
All right, thank you.
Okay, thank you. Now, the last thing, which is to calculate the currents. How to calculate the currents? We know VSA equals VAN times IA conjugates. How about to calculate IA? IA equal to SA over VAN, all of it conjugates. So it's going to be as 7.68 times 10 power 3, angle 30 degrees, divided by VAN 277.1, angle 0, all of its conjugates. So when you do this, the analysis, do inside the brackets first. So it will be 27.71, angle 30 degrees. Then do the conjugate at the end. Don't forget the conjugates. This is one of the common mistakes. Then after that, let's do the conjugate. It will be 27.71, angle negative 30 degrees, amperes. This is IA. Okay? How about IB, IC? Since it is positive sequence, we can say IB will be 27.71, angle negative 30 minus 120, negative 150 degrees amperes. Then IC will be 27.71, negative 30 plus 120 will be 90 degrees amperes. Then problem done. We'll go here. Any question? Okay, now we are done with the complex power. The next topic will be the power transformer. And let me write some recommended textbook problems. Which is problem 826, 828, 829, 831, 832, 833, 837. Okay?